You have already learned that the rate of a reaction decreases with a decrease in the concentration of the reactants. Thus, one of the factors that determine the rate of a reaction is the concentration of the reactants. The representation of the rate of a reaction in terms of the concentration of its reactants is known as the rate law. It is also called the rate equation or rate expression. It is important to note that we can determine the reaction rate in terms of the concentration of the reactants only by experimentally, and it cannot be determined from the balanced equation. Consider the reaction given here. Let's say m moles of A react with n moles of B to give O moles of C and P moles of D. We can write the rate law for this reaction as rate of reaction is directly proportional to the concentration of A raised to the power x multiplied by the concentration of B raised to the power y. By replacing the proportionality with proportionality constant K, the equation can be written as shown. The K in this equation represents the rate constant. The exponents x and y may or may not be equal to the stoichiometric coefficients m and n of the reactants A and B, respectively. This expression, which relates the rate and concentration of the reactants, is called the rate law or rate expression. Thus, rate law is the expression in which the rate of reaction is given in terms of the molar concentrations of the reactants, with each concentration being raised to some power that may or may not be the same as the stoichiometric coefficients of the reacting species in a balanced chemical equation. You know that the rate of a reaction with respect to the reactants is equal to minus dr by dt. Therefore, the equation can be written as minus dr by dt is equal to K multiplied by concentration of A raised to the power x multiplied by the concentration of B raised to the power y. This is known as a differential rate equation. In the given rate equation, x is the order of the reaction with respect to A. Y is the order of the reaction with respect to B, and K is the rate constant. Also, x or y is usually a whole number integer, such as 1, 2, 3, or fractional. The sum of the exponents x and y gives the overall order of the reaction. Thus, the order of the reaction is defined as the sum of the powers of the concentration terms in the rate law. It is important to note that the order of a reaction can only be determined experimentally and not from the coefficients of the balanced equation. For any reaction, the reaction rate with respect to the reactants is determined by varying the concentration of any one of the reactants, keeping the concentration of other reactants constant. Let us look at a reaction to understand this better. Consider the reaction of acetone and bromine. Using the data in the table given here, it is possible to calculate the order of the reaction with respect to both bromine and acetone. Let us see how the rate of reaction changes with a change in the concentration of either bromine or acetone. From experiments 1 and 2, it is obvious that there is no change in the rate with a change in the concentration of bromine. For experiments 1 and 3, it is obvious that the rate is doubled as the concentration of acetone is doubled. That is, the rate depends on one concentration term with respect to acetone, while it doesn't depend on the concentration of bromine. Thus, the order of the reaction gives the mathematical relation between the reaction rate and the reactant concentration. If X is equal to 0, then it is a zero-order reaction with respect to reactant A. Similarly, if X is equal to 1, then it is a first-order reaction with respect to reactant A, and so on. Similarly, if Y is equal to 0, then it is a zero-order reaction with respect to reactant B. Also, if Y is equal to 1, then it is a first-order reaction with respect to reactant B, and so on. Thus, the sum of the exponents, X and Y, gives the overall order of the reaction. Let us write the rate equations for all the three experiments. For experiment 1, rate 1 is equal to K multiplied by 0.1 to the power Y multiplied by 0.1 to the power X. Let this be equation 1. For experiment 2, rate 2 is equal to K multiplied by 0.2 to the power Y multiplied by 0.1 to the power X. Let this be equation 2. For experiment 3, rate 3 is equal to K multiplied by 0.1 to the power Y multiplied by 0.2 to the power X. Let this be equation 3. Dividing equation 2 by 1, we get rate 2 by rate 1 is equal to K multiplied by the concentration of bromine in experiment 2 to the power Y multiplied by the concentration of acetone to the power X, divided by K multiplied by the concentration of bromine in experiment 1 to the power Y multiplied by the concentration of acetone in experiment 1 to the power X. On solving for Y, we get Y is equal to 0. Therefore, the order of the reaction with respect to bromine is 0. Similarly, we can calculate the value of X by dividing equation 3 by 1. We get X as 1, which gives the order of the reaction with respect to acetone as 1. The overall order of the reaction is therefore 1 plus 0, which is 1. We can calculate the value of K by substituting Y and X in any one of the three equations as shown. Therefore, we get the value of K as 1.64 multiplied by 10 raised to the power of minus 4 per second. The units of K depend on the overall order of the reaction. If we rearrange the rate equation for K in a generic reaction, we get K is equal to rate divided by the concentration of A to the power X multiplied by the concentration of B to the power Y. Representing this equation in terms of the units of concentration and rate, we get the unit of K as rate of the reaction divided by concentration to the power Y plus X, where Y plus X is the overall order of the reaction. The unit for concentration in the SI system is mole per liter. If Y plus X is 0, then we get the unit of K in the SI system as mole per liter per second. If the overall order of the reaction is 1, then we get the unit of K as per second. If the overall order of the reaction is 2, then we get the unit of K as liter per mole per second.